Hello, everyone. Today we are going to talk about hyperbolas. Hyperbolas is another class in a family of conic sections. Remember, we covered ellipses in the previous lecture. And what I'm going to do, guys, first I'm going to start with definition. And to show that hyperbolas are very close to ellipses, I'm going to copy definition of an ellipse. Remember, an ellipse is a set of all points in the plane, the sum of whose distances from two fixed points is a constant. I'm going to modify it a little bit and make it a definition of hyperbola. I'm sorry, I need to put it over here. What is hyperbola? Well, we already have a sum of the distances from 2 points equals to a constant. Now, guys, we are going to make a difference of 2 distances equal to a constant. And that's going to produce a hyperbola. Let me show you like what kind of expression we're going to have. Remember, for ellipse, we have distance 1 plus distance 2 equals to a constant, right? For hyperbola, we're going to have distance 1 minus distance 2 equals to a constant. And that's going to produce a totally different curve. Now, guys, we remember that equation of an ellipse was x squared over a squared plus y squared over b squared equals to 1, right? Well, remember that we obtained this equation using directly distances and squaring the expression for this distance equals to a constant couple of times. Same way we can obtain equation for hyperbola. But because it's kind of a long process, you can always look up in your book how we obtain this equation. The steps are almost same. The only difference is going to be one extra minus. So I'm not going to do it in lecture. I'm just going to give you an equation. And I hope that you can try on your own to get this equation without my help. The equation is going to be very similar to equation of an ellipse, just instead of plus, like we have for an ellipse, it's going to have a minus. Again, if you start doing the equation from like basic geometry and distance formulas, the only difference is going to be that in certain places you are going to have minus, and eventually there is going to be minus in front of y, and that's it. What is what over here, guys? Let me kind of set up, like, remember for ellipse, b square, this one, was connected to this a, which is half of the length, which is like the constant over here, right? The constant here is 2a. The constant here is also going to be 2a. Right? What was b square? The b square was a square, the half of this sum distances, minus c square, which was distance from the middle to the focal point, right? Or like half of the distance between focal points. What is going to be b over here? Well, b over here is going to be very close to that b, but it's going to switch actually positions c and a. It's going to be c squared minus a squared. Again, c, it's a distance between focal points. You have focal point 1 and you have focal point 2. And this is a distance to c. So c is half of this distance. And a is equal to the half of this constant, which is a difference of distances. Well, interestingly is that the curve we are going to have is a very different one. And I'm going to kind of show you like right away the picture of that curve. Well, guys, how do we usually graph hyperbolas? Well, we are going to build something which is called a fundamental rectangle. Fundamental rectangle is a rectangle which has x dimension equals to a and y dimension equals to b. And please watch how I build this fundamental rectangle. First, we are measuring a units in x direction, and b units in y direction. Well, I'm obviously using like 3 and 2, but actually can be any number. Okay, so it's a and this is b. And then we are going to build a rectangle through these points. And through the corners of this rectangle, we are going to draw straight lines. These straight lines are going to make slant asymptotes of hyperbola. Slant asymptotes are lines to which hyperbola is going to approach at infinity. And now we are ready to build the hyperbola itself. So I'm going to start from the one of the sides of my rectangle and one of the sides here and one of the sides over here. That's a picture of a hyperbola. Okay, that's like the set of steps we are going to do. Where on this hyperbola are focal points? Focal points are going to be somewhere here. That's going to be focal point 2, and this is going to be focal point 1. You see the difference in ellipse? They were kind of inside of the ellipse, and these 2 points are outside of fundamental rectangle. For asymptotes, usually you just, if you graph rectangle and draw diagonal lines, that's going to be asymptotes. I'm going to prove that they're asymptote, but a little bit like later. Let's first practice in graphing hyperbolas. So let's consider a couple of examples, and then I'm going to consider proof of asymptotes. So example number 1. X squared over 16 minus y squared over 9 equals 1. So we know that x dimension is going to be 4, right? And y dimension is going to be 3. They are square roots of 16 and 9. That's 4 squared, and this is 3 squared. Then you graph fundamental rectangle and draw carefully your hyperbola. So we have 4 units here, right? 4 units here, 3 units here, and that's going to be fundamental rectangle. You don't really need to graph a rectangle. It's just like, usually we graph it just to make sure that we don't miss a point or whatever. Normally, guys, the only thing you need this point and this point and asymptotes. This is 3, this is y, and this is x. And I'm going to use blue color and graph it like this. Okay, so these 2 points are going to be x-intercepts, and hyperbolas are not going to, both branches are not going to have y-intercept. Why? Well, if you set up y equals to 0, what are you going to have? You're going to have x squared over 16 equals to 1, from where x squared equals 16 multiplying by 16, or x equals plus minus 4. That's exactly what we have, right? But if we set up x equals to 0, if we set up x equals to 0, we're going to have minus y squared over 9 equals 1. Well, you understand that minus y squared equals 9 is not going to give you any real solution. No real solution. So no y-intercepts. Because of this. You cannot find a number which you square and then put minus and get 9. You see? Okay, not all hyperbolas are going to be what I call horizontal hyperbolas. Let's graph some other hyperbola, which is going to be vertical. But for this one, let's find a focal point. Where is focal point going to be located? Remember that for hyperbola, the relation between b and a and c is slightly different. B is equal to c squared minus a squared, right? So my b is like 9. B squared, right? That's 3 squared. And my c is unknown, and my a is like 4 squared is 16. So what is going to be my c squared? My c squared is 9 plus 16, or c equals plus minus square root of 25 or 5, right? Is it 25? Yes, 25. Okay. So actually the focal point over here, sorry, and the focal point over here. We're going to label focal point 1 and focal point 2. Okay. One more example of hyperbola, and then I'm going to talk about asymptotes, okay, a little bit, because asymptotes are slightly more complicated. And let me consider another example. Example 2. Well, let's consider hyperbola y square minus 4x square equals 4. You see that over here, it's not equal to 1, there's 4. How do we kind of work with this obstacle? We're going to divide by 4 both sides, and then it's going to turn into 1, and we have y square over 4 minus x square equals to 1. Fundamental rectangle. X dimension is going to be what? What is under x? Under x is actually 1 square, right? So x dimension is 1, y dimension is 4 is 2 squares, so it's 2, and we graph fundamental rectangle. I'm going to graph it over here, okay? So I'm sorry, I keep pressing something on my panel and makes me, oh, let me graph a little bit better my axis, because my y-axis sits in the middle of the squares. It's not going to look very nice if I graph. So I have x dimension 1 unit and 1 dimension 2 units. Maybe, you know, guys, I'm going to do x dimension a little bit bigger, like 1 unit here and 2 units here in y dimension. So that's going to be my fundamental rectangle. Minus 1, that's 2, minus 2, and asymptotes. Sorry. X over here and y over here. So now, how do I place my hyperbola? Remember, guys, we always need to check intercepts. If we look back at the equation of our hyperbola and set up x equals to 0, we are going to have y squared over 4 equals to 1, or y squared equals to 4, or y equals plus minus 2. So when x equals to 0, y equals plus minus 2. I'm going to put 2 blue points. It's plus 2 minus 2. If I set y equals to 0 to find y-intercept, I'm going to get 0 minus x squared over 1 equals to 1. And this one is not going to have any real solutions, because we have minus a positive number equals to 1. No real solution. So there's going to be no x-intercept. And because there are no x-intercepts, the hyperbola is going to look like this. Well, sometimes people just memorize that when y comes first, the hyperbola is vertical, and when x comes first, the hyperbola is horizontal. But also, you can always check intercepts. You are not going to get two sets of intercepts, because hyperbola is either horizontal or vertical, and the second set is going to give you no real solutions. And that's how we graph hyperbolas. Okay, now I promised to talk a little bit about asymptotes. Let's discuss asymptotes, like maybe in general, a little bit just. Well, I'm going to consider something like a regular hyperbola equation and kind of discuss what happens to this hyperbola equation, why we do have this asymptotes. Well, imagine that we have x squared over 25 minus y squared over, let's say 9 equals to 1, typical hyperbola, right? Now, if I solve this equation for y, what I'm going to have? I'm going to bring y on one side. Y squared over 9 equals 1 plus x squared over 25. What I did, I brought y over here, and I brought 1 over here. And sorry, it's supposed to be minus 1. Minus 1 here. Okay. What I can do next? Well, I can extract the square root from both sides. I'm going to have y equals square root of x squared over 25 minus 1, right? Well, it's supposed to be plus minus, because we are extracting the square root. And the square root of 9 over here is going to be 3. Now, guys, what is going to happen when x will go to infinity? When x goes to infinity, this x squared will be a big number, right? And this 1 is going to be very little in comparison to a big number. So we are going to drop it. Sorry, my board is kind of drop. What we are going to have, guys? We are going to have y over 3 equals plus minus a square root of x squared over 25, or plus minus of x over 5, right? If you extract a square root. So y actually is going to become 3 over 5x and plus minus, which is going to be equation of a straight line, and that's going to be asymptote actually, right? So what is 3 over 5? 3 over 5 is going to be a slope of this straight line. And if you graph the fundamental rectangle with like for this, it's going to be 5 here, right? And 3 over here, right? And if you graph the line, which I was graphing as asymptote, what is the slope of this line? Well, rise, which is 3 over 1, which is 5. And that's exactly 3 over 5, right? And that's why we have these two lines as horizontal asymptotes, because when x goes to infinity, the y is not going to be a curve anymore, but it's going to look very much like that straight line. Why do we have plus minus? Well, because we do have the second asymptote. This asymptote is going to correspond to plus answer, and this is going to be minus. So it's minus 3 over 5 and plus 3 over 5. My suggestion, do not worry too much about finding actual asymptote, but draw fundamental rectangle and use it to graph the hyperbola. Okay. And I think I'm going to consider one more example of hyperbola, just to give a little bit more examples, and that's going to be all. So example number 3. Guys, imagine that we have something like 25x squared plus 4y squared equals 1. What if our hyperbola looks like this? So it's supposed to look like, sorry, it's supposed to be minus here. Minus. It's supposed to be x squared over a squared minus y squared over b squared equals 1, right? But we do have something like multiplication instead of division. Well, we should remember that every multiplication can be represented as division by a fraction. If you simplify this, that's going to be 1 multiplied by 25 over 1, right? So you always can put this 25 in denominator, but that's going to make up a fraction. So if we do this, we are going to have x squared 1 over 25. Same with 4. And you can use it for ellipses too. Y squared 1 over 4 equals to 1. We did not multiply anything by anything. We just placed this 25 in denominator. And 1 over 25, it's 1 over 5 squared, right? So my x dimension then is 1 over 5. And 1 over 4 is 1 over 2 squared. So my y dimension is 1 over 2. And my fundamental rectangle is going to have very small dimensions, but still, it's going to be a nice fundamental rectangle. So 1 over 5 is less than 1 over 2. So I'm going to label somewhere here 1 over 5. Let me make it like nicer. So let's imagine that this is 1 over 5. Negative 1 over 5, and 1 over 2 is about like twice bigger, right? It's supposed to be somewhere here. Well, I'm trying to make it as nice as possible. And draw asymptotes. Now, what is going to be vertical or horizontal? Again, if you set up x equals to 0, then y won't have any solution because it's going to be negative y equals 1. It's possible, right? But if you set up y equals to 0, you are going to have that 25x squared equals to 1, from where x equals 1 over 25 and the square root and plus minus. Right, so that's exactly what we have over here, 1 over 5 and 1 over 5. So it's horizontal one. Okay, let me graph it over here. Guys, don't forget that your hyperbola should approach your asymptotes like closer to infinity. So I'm not supposed to go away from them. Let's label 1/2, 1/5 here. Okay, so that's how we deal with hyperbola like this. Okay, usually, guys, I'm not going to ask you to calculate the focal point, but you know the formula, right? The formula is like for an ellipse, just A and C are switched, and you can always calculate. Remember that for hyperbola, focal points are going to be over here and over here inside of the hyperbola. Okay, like focal points for hyperbolic antennas are inside of them, right? Okay, well, do your homework, and I'm going to meet you again. Next lecture is going to be about shifted conics.